Hello, welcome. We're going to be looking at problems in energy transfer or energy transport. We are taking this example one. One side of a plane wall. This is a plane wall. This is one side, this is the other side. One side, the other side. One side of a plane wall receives uniform heat flux of 500 watts per meter squared due to radiation. So there is radiant energy hitting this side of the wall with the flux of 500 watt per minute per meter squared. Radiant energy, maybe from the sun or somewhere else. The other side dissipates heat by convection to the ambient air at 25 degrees Celsius with an average heat transfer coefficient of 40 watt per meter squared. So this other side is giving air. You can see air here. This other side is giving air at a temperature of 25 degrees Celsius and heat transfer coefficient of 40 watt per meter squared Kelvin. Now, if the thickness and the thermal conductivity of the wall is 15, the thickness, distance between the faces, 15 cm, and the thermal conductivity K of this very wall is 10 watt per meter squared Kelvin, respectively. Calculate the surface temperature under the steady condition. So find out the temperature here and the temperature here. What is the surface temperature? Temperature on this first one is T0, whereas temperature on this other side is TL. So that is what you want. They want you to calculate. Calculate the surface temperatures. So before you start, you make an initial assumption that this actually is taking place only in the Z direction. And at steady state, the differential of T into two places is always 0 with respect to the dz. So what do you do to this? What you're going to do to this is that you're going to integrate 2 times since this is squared. So if you're integrating for the first time, you integrate this and integrate 0. If you integrate empty space or empty or 0, you get a constant and another 0. So that is what we did here. We integrated this one by putting the integral. Integrated this one by putting the integral. If you integrate this, you have only the t dz. Instead of the squared t dz, you have only the t dz. If you integrate 0, you have 0 plus a constant. So this is what you have now. But you're trying to get the expression for temperature alone. You don't want d. So you have to integrate again. So when you integrate this one, this very one, you also integrate this constant. 0 is 0, so it has gone. So now when you integrate this, you get t, ordinary t. When you integrate this one, this constant, you get constant. No. There is a mistake, please. This is supposed to be integrating this plus also integrating 0, because this is this and 0. Now, when you integrate this, you get only t. When you integrate a constant, you get that constant times the factor that you're integrating with respect to. So that's why you have C1z. Then when you integrate 0 again, you get another constant too. That's the way you integrated this 0 here to get a constant. You understand? And 0. So this is what you have. So you can also add 0, but this is actually what you have. T now is equal to C1z this. So when you look at this equation very well, you see temperature is equal to, this is a function of z. Function of z. Whereas this one is just an ordinary constant. So when you're looking at this very geometry, the geometry of the wall that you're talking about, now, in place of this t, you are told to find the temperature here. That's T at this surface and T at this surface, TO and TL. And you already know the expression for temperature. So just fix back either of these to get this. So for TO, you are going to put in place of T, now you have it TO. And it's equal to a function of Z. A function of Z. So it has to be a function of temperature here, and that is the initial or the T infinity. That's what we are going to be having here. Plus a constant. So this is constant. Constant here is the expression for Q0 multiplied by something, depending on the side you're picking. So if you're picking for here, it's going to be 1 over h plus L over K. L is the distance and this one is the constant here. And if it is here, you're just saying Q0 bracket 1 over H only. So that is what we have. So this expression is the same as this, only that we're replacing T with TO. This temperature, which is the ambient temperature 25, plus a constant. This constant is Q. For TO is going to be QO in bracket 1 over H plus L over K. While for TL it's going to still be the same thing. Put this ambient temperature. Put also Q the way you put Q. But instead of having 1 over H plus L over K, just have 1 over H. So this is what you use in finding TO, and this is what you use in finding TL. So now you already know all these things. So you just to substitute all of them inside to get your TO and TL. Because T infinity or ambient temperature is simply 25. So if you add 273, you get it in Kelvin. Q, you're already given QO is 500. K, you're already given is 10. L, you're already given is 15 cm. It converts to meter, it becomes 0.15. So when you substitute into this, you get TO to be 45 degrees Celsius. That's when you convert back to Celsius. If you substitute into TL, you get it to be 37.5 degrees Celsius. So you see, very, very importantly, when you look at this, you draw this. So once you draw this, you identify what they want you to find, surface temperatures, TO, TL. So you are now looking for expression for this so that you can find it. And at steady state and only in the direction of Z, this is the partial integral of this with respect to dz. So that's why we're having dz squared equal to 0. So integrate 2 times. The first integration you do, integrate this, you get only this. Integrate 0, you get 0 plus constant. Very, very important. So you now integrate this one again, so that when you integrate this one, you get T. Integrate 0, you also get 0 and a constant. This is constant plus 0, but since you are not integrating again, you left it. Integrating a constant, you have that constant times the factor that you're integrating with respect to. So this is the expression you want, and that is what you get. Since you found the expression for T, that expression for T can be used in getting TO or TL when you do the right substitution. So in place of T, put TO. In place of T, also put TL to find TL. This is a factor of must be a factor of the independent variable, and that is temperature, ambient temperature. So you put the two together. You put the two for the different ones, whether you're getting for TO or TL. Now the constant is this. That's where varies because of the geometry of this. You put Q in multiply by something. This one Q multiplied by something. But here Q is multiplying 1 over H plus L over K, whereas here Q is multiplying 1 over H alone. So substitute the values of what is given, and you get your TO and TL. So that's how you solve this. Please, if you have any question, drop it in the comment section. Like, share our videos. Thank you and God bless you.